My name is Sam Reifenstein, and I'm a research scientist at NTT Research. In this video, I will summarize our ICML paper titled Dynamic Anisotropic Smoothing for Noisy Derivative-Free Optimization. So we start with a classical problem where we're given an unknown objective function and a noisy oracle, and we're trying to optimize it. And a key property here is that this noisy oracle only has access to the function and not the gradient. Thus, we call this noisy derivative-free optimization. There are many existing approaches to this problem, and it's well studied in the literature. For example, many people study this in the machine learning community as a alternative to backpropagation to train neural networks. These methods are typically called gradient estimator methods. There are also many traditional zeroth order methods that can be extended to the noisy case, such as Nelder-Mead, trust region methods. And then there's also Bayesian optimization, which is commonly used in machine learning to tune hyperparameters. But all these different approaches have their limitations when it comes to very noisy objective functions, heterogeneous curvature of the loss landscape, and larger dimensions. So our specific motivation for this work is a certain type of optimization. So combinatorial optimization is known to be NP hard in some cases and very difficult for computers to solve. So people tend to use heuristic approaches to these types of problems. And these heuristic algorithms, they have some probability of success and have parameters. And so to tune these parameters, you end up with a very noisy derivative-free optimization problem. And we found that these types of optimization problems have certain properties, such as large noise, heterogeneous curvature, which means like a complicated relationship between the different parameters, and an intermediate to larger number of parameters. And these properties made the existing methods I talked about in the previous slides to not work very well. So this motivated us to try to design a new approach. So our approach is based on the work of Nesterov in 2017. And basically the way their method works is they have this is a gradient estimator method. So basically what they do is you have a guess for your optimum of the objective function, x, and you choose some distribution to sample points around it randomly. And for each of those samples, you get a noisy evaluation of the objective function. And you can use those noisy evaluations to estimate the gradient of a smooth version of the objective function. And then you can do gradient descent. So basically, our work is very similar to this. The main thing that we added is now this distribution of where the points are sampled, which we call the sampling window. We now update it dynamically, which allows it to change size and shape depending on the samples. So for example, this is an example of how it would work when optimizing a function known as the Rosenbrock function, which is a commonly used function in optimization theory. So you start, unlike other gradient estimator methods, you start with a very large sampling window. You make some samples in it. Based on the samples, you then move and shrink and change the shape of the window. And then you make more samples and repeat the process and eventually zoom in on the optimum. And we found that this type of approach that we designed tended to work better on these really complicated test functions like the Rosenbrock function, where you have a very complicated relationship between the different dimensions. And it seemed to work better than previous methods. So to go into more details on how the algorithm works, basically it's based on these stochastic differential equations, which govern how the window position and window shape evolve. And this SDE can be understood as being based on stochastic gradient descent, but we also, first of all, we add a preconditioner to the gradient which comes from this L matrix, which also governs the sampling window shape. And then we also add dynamics to update the sampling window based on the noisy samples. So more specifically, if we look at this SDE, what we find is that if we look at the fixed points of this SDE, what we find is that at a steady state, just like gradient descent, we end up with a local optimum of the smooth objective function, which is great. And we also find, as kind of the new thing of our algorithm, that this matrix L, which governs the window shape, ends up converging to a scalar multiple of the inverse Hessian. And this is great because we know that since we're using it as a preconditioner, we know that using an approximate Hessian as a preconditioner is what is known as a quasi-Newton method, and is a common method when you have these complicated energy landscapes, and people study this a lot in machine learning as well. We also numerically studied the asymptotic convergence of our algorithm, and we found that the scaling of the error with the number of samples reached this theoretically known optimum, which is number of samples to -1/2. And this is kind of a theoretical lower bound when you have the noisy evaluation. And we also found that scaling with problem dimension, that is the number of parameters, was pretty good, at least in the smaller dimensions we looked at. And then lastly, we have some numerical results on the specific application that we're interested in, which is tuning the parameters of these combinatorial optimization heuristics. So we have two examples here. One of them is a Boolean satisfiability solver on the left, and then also an Ising solver on the right. And we found that our algorithm is able to find better parameters in fewer samples, so less computational time, than these other existing algorithms that we looked at from different fields. So lastly, for some outlook and future directions, one of the motivations for this work is we wanted to draw a parallel between recent advances in combinatorial optimization, which use what we call differential solvers. And these differential solvers, they have many parameters that need to be tuned, like I said, but they also show mathematical parallels to things like recurrent neural networks and graph neural networks in machine learning. So being able to tune the parameters of these algorithms is essentially parallel to training the parameters of certain types of neural networks. So we wanted to make that connection, and we also wanted to see if our algorithm, once we tested it out, was going to be possibly useful for training much larger models. And one reason it might be useful is because its ability to compensate for this heterogeneous curvature of the energy landscape. So that's all in here. If you're interested, here's the paper and here's the code. Thank you for listening.